So hello and welcome to our tutorial on ANN without TensorFlow and Keras. So in this video we are going to try and going to deliver, make the backpropagation function. So let's just open our previous file ANN it was, and here it is. So now let's just increase the font. First let me maximize this and increase the font. Sixteen is great, I believe. Okay, so this was what we did last day. So after the feed forward we will move forward with the backprop portion. Now remember, backprop is the most important part, and we must learn everything very slowly and must keep in mind. So we just define some parameters now. If we find that if we need anything else, we need some more parameters, then we will declare it later as and when we require. So now LR is the learning rate. I guess this is all. Okay. So the backprop portion, let's first just find the equation, or learn the equation how to find the backprop, and then we'll move forward with it. So these were the equations of our feed forward network that we have used last day. So basically our backprop was just the opposite of this, but definitely there are certain different equations. Let me just clear these, we don't require it anymore. Okay, and yeah, so let me use the pencil, and give me a minute. Okay, so Z will be equals to sigma x, where sigma is actually, it signifies the sigmoid function. Now what is the sigmoid function, you will come to know a bit later. Now basically Z here forms our function after the activation function is carried out. Okay, so what are our weights? Our weights will be our initial weights, which is W, minus the alpha, which is the learning rate, multiplied by dW. Now what is this dW? What is this dW in particular? So let's find out what is this dW. dW is actually dJ upon dW. Now what is this J? J is actually the cost function. So J is actually the cost function and W is definitely the weights. So a differentiation of a cost function with respect to weights forms something like this. No, let's just stick to Z itself. Why, because here we'll be actually using the symbol Z, but definitely keep it in mind that J and Z are actually both are the cost functions itself. J normally is used in machine learning portions, and Z here in deep learning portions we are using. It's nothing different, both are variables, and for now just assume J is equals to Z, and hence we are replacing it. So now dz upon dx into dx upon dw. This is a required uh, equation. So now this is using the chain rule, definitely dz upon dx, and then further the dx upon dw, the portion that we are using the chain rule there. Okay, so now what is x? X is actually what we say is a function of the weights inputs, and definitely it is a function of bias. uh, so this is the sigmoid function, 1 divided by 1 plus e to the power of minus x. 1 divided by 1 plus e to the power minus x is the sigmoid function, because we have taken sigma of x here. We will just use, okay, I have written x equals to this, so that would be z equals to this. One moment, I'll just change it. This is z, the variable should be z, because we have defined z equals to sigma of x. Okay, so this is our sigmoid function. Now what is x? As I said, x is equals to a function of w, I and b, where w are the weights, I is the input. So here this comes our x equals to w into I plus b. Okay, so now that we have these equations, let me just clear this portion off. Okay, I guess we are good to go now. So after we have these equations, we are going to put it into our main equation. Now what is our main equation? Our main equation is dz upon dx. I mean, this is not the main equation, but actually this is the transfer derivative function, so we need to differentiate here. So that's why I'm calling it at the main equation. I mean, this is the main function that we need to go through. So this will be 1 plus e to the power minus x whole square to the, I mean, in the numerator it will be 0 minus d dx of d upon dx dx of 1 plus e to the power of minus x. Makes sense? This is the differentiation of u by v formula. Okay, so I believe you are all aware of it. And then on differentiation it forms e to the power of minus x, and with the chain rule again it forms minus 1 divided by 1 plus e to the power of minus x whole square. Okay, so now the minus outside and the minus 1 will be multiplied. Let me just remove these portions. I hope you are through with it and we don't require it now. Okay, so I'll just pull it off here, and this will give us dz upon dx equals e to the power of minus x So this is e to the power of minus x divided by 1 plus e to the power of minus x whole square. So after this, what we'll do, we'll arrange this a little bit, like will form 1 divided by 1 plus e to the power of minus x, and we'll make this as one term multiplied by e to the power of minus x divided by 1 plus e to the power of minus x. So if you just compare it, both the left hand side and the right hand side are the same. We have just arranged it a little bit. So now 1 divided by 1 plus e to the power of minus x is our sigma x, or the sigmoid function of x, as mentioned here. Here we have used z, which is actually is sigma of x itself, so we can write in both ways. So what now, the 1 plus e to the power of minus x, what we do is, with the other term we add 1 and we subtract 1. After adding 1, we separate it and segregate it, and here it forms 1 plus e to the power of minus x divided by 1 plus e to the power of minus x minus 1 divided by 1 plus e to the power of minus x. So what I suggest you just take some time, pause the video and check it whether both the terms are same or not. You will just find that both are practically the same thing, just rearranged a little bit. Okay, so after we take these values, and we can finally conclude that dz by dx is equals to sigma of x, or z for that matter, because we have considered it as z also, multiplied by 1 minus sigma of x. So this is the derivation of a sigmoid function. This is very much required if you use the ReLU activation layer. So after you have tried it with sigma, please try it with ReLU as well if you want to use the ReLU layer as your activation function. So now we'll select this and move it here. Also what we'll do, we'll select the actual derivation of which value it is being used for. Clear it up here. Okay, so now what x was represented as, x is equals to w dot I plus b. Okay, so we represent that in that way. Okay, so dx by dw will be actually del x by del w if we consider all the other parts as constant, because at a time in a multivariable differentiation operation we can at a time consider only one as a variable, and we have to consider the rest as constant. So it will be practically equal to del x by del w, keeping b as constant, so it will give us I itself. Okay, so hence what we can conclude, that del x or dx by dw is actually equal to I. Thus what we need to find is dj by dw. So one might find this awkward, that why am I using dj in place of dz. Means previously also I have used dj in place of dz, and now I have made it equal to dz. Actually j is the standard variable or the standard notation for cost function, and since here we are dealing with the cost function, that's why we have used. Anyway, dz by dw is equals to dz by dx multiplied by our del x by del w, or actually it is dx by dw, but definitely when our base and I is though definitely is constant, and our bias p is when it is constant, then it will become del x by del w itself. Okay, so finally what is the output we are getting? We will be getting sigma x into 1 minus sigma x multiplied by I. Okay, so this is what our transfer derivative is. Actually our transfer derivative, will discuss the transfer derivative later. So our w will be w minus alpha, alpha being the learning rate, dz by dw. So after we put the value of dz by dw, it will become w minus alpha, and let's just select it. Oh sorry, selection is difficult because the dot of I is missing here, so we'll just put it manually. It's looking like C. I'll just put it here manually, and yeah, this is our final equation. So we'll just note it down, put a box and note it. So this is our final equation that we will be using for our backprop. Let's go back to our editor and we can code for our backprop. But before going for the backprop, let's just first define the transfer derivative. Now I was talking about the transfer derivative before this, so we just define it and then I'll explain it to you what is the transfer derivative. So since it is an OOP, so we need to have the self as a compulsory parameter and z the other parameter. It will return z into 1 minus z. Okay, so this is our transfer derivative. Actually what we have here, like check out that dx by dw that we have used is equals to sigma x to 1 minus sigma x. That is actually the parameter which is the transfer derivative. This here is our transfer derivative. Still, let me write it down so that you can note it. Transfer derivative. Okay, so this is very important. Now after we have done with the transfer derivative, let's clear it out a little bit. After we have dealt with the transfer derivative, because we need the transfer derivative for both back propagation for weights as well as for back propagation of bias. Okay, so now this we have to do it for, we have to deal with the bias, because bias also is a random variable and we need to find the actual variable that will provide us with the expected result. So dz by db, now it will be, initially it was dw, now it will be db. So this will be initial bias b minus alpha, which is the learning rate. Let's write it properly. So we'll just we'll just jump directly. Okay, so we'll just jump directly to the equation. It is sigma x into 1 minus sigma x. Uh, so this we were aware of into 1. Now why 1? So this is our final output that we'll be getting. So how are we getting this output? We'll just check it. So dz by db will be equal to our dz divided by dx, taking x as our the value of this that will be used as the a sigmoid parameter. I mean, after the activation the value. So dx is equals to, I'm sorry, dz by db is equals to dz by dx into dx by, should, it is db, I've written b I believe. So okay, it's understandable. Okay, so x is w dot I plus b. So when we find dx by db, that will give us del x by del b keeping our weight as constant. Okay, so this will give us 1. Now this one will be brought here. This is where we get the 1 from, and definitely sigma x into 1 minus sigma x, as we have done earlier. I'll just write it down still. Dz by dx, as we have done in the last video, it will give us sigma x into 1 minus sigma x. If you want to check how this value comes, you can just go backward, and you can check the derivation of weights. So where we have derived it for weights, and it will tell you how we are getting this value sigma x into 1 minus sigma x. So copying this is a bit problem. I'll do one thing, I'll just write it down. Sigma, okay, don't think that this is 6, okay, because it is pretty difficult to write sigma here. I'm just assume that this is sigma of x. Sigma is a Roman symbol, so you just think it is sigma of x, not 6 of x. Some people will think that this is 6x into 1 minus 6x, but it is not. So this is our final derivation. What I want you to do is note both the values of dw and db down. Note both of them.